Welcome back. So this is day 2 of section 1.3, all about transforming functions. Transforming functions. The title is New Functions from Old Functions. All right. It's funny. I don't know what class is doing it right now. It's probably the honors algebra 2 classes that are doing it right now. But I feel like I've helped a lot of students recently transform functions. Like they've been coming up to me like, Mr. Schreiber, how do I do this? And they've got the like horizontally stretch or compress or whatever it may be. And they're working with absolute value and linear. So, but these are ones that we've done before, right? We talked about all of these functions, all of these transformations of ones that we have done before. We've done this before, but what we're going to do now is just say, generalize it to say, okay, these are shifts up and down. Let's say anything that you could possibly throw at us, that's going to shift it up or down. These are going to shift it left or right. Any type of function. These are going to stretch it or shrink it vertically. These are going to stretch it or shrink it horizontally. These are going to reflect it. So we can take any type of function and do these transformations on that function. All right, shut up and get to it, Mr. Lever. Sketch the graphs of the following functions. So I am going to sketch the graph of y equals sine 2x, and then we're going to sketch the graph of y equals 1 minus sine x. Now, I would love to be really exact, and you could get into, like, we could plot a lot of points when graphing these. It's always good to graph at least one period of sine or cosine, or tangent for that matter, anything trig, anything periodic, I guess. It's always good to graph at least one period of this. But here's the goal for this. I want you to be able to look at the look at the equation and be able to tell what's going to happen and to visualize that. Okay? Like for example, y equals sine 2x. What should happen from the parent of y equals sine x? What should happen? Can anybody tell me what should happen? Good. A horizontal compression. I like that he said compression. Even though you see a 2x on the inside, because it's on the inside, that's actually a compression by a factor of 1/2, right? So I should see my regular sine function just get smushed horizontally in toward the y-axis. All right, so let's actually take a look and see if that does happen. And I'm just going to sketch a graph of one period here. Let's, for good measure, let's just graph sine, right? Remember, sine starts at the axis, right? And then one full period is 2 pi. And it goes up to 1. And then down to, that kind of rounded out a little bit more on the bottom. But you get the idea. Just a sketch, folks, just a sketch. Looks a little more oblong than I'd like, but that's okay. And it goes down to -1 and up to +1. What is this coordinate in the middle here? Where is that? Pi, right? There's pi. And where is it peaking? Where's it peaking? Pi over 2. And 3 pi over 2, right? There's the value. Why is that the case? Because think about it again. In the y value, it goes up to pi over 2, up to 90 degrees, and that's as big as it gets, right? It goes up to +1, the y value. And then it goes over to pi. I guess I should rotate it this way for you guys. And then it goes over to pi, and the y value goes to 0 again. And then it goes down to 3 pi over 2, where the y value is -1. And then it goes back to 2 pi, where the y value is at 0 again. Okay, so that was just sine of x, right? Now let's do sine of 2x. Sine of 2x. Now, thinking about it logically, as a horizontal compression by a factor of 1/2, it's just going to take all of those x values and multiply them by a factor of 1/2. So where is this 2 pi going to go? Back to pi. Where is pi going to go? Back to pi over 2. Right? This point gets shifted to here, or I shouldn't say shifted. This point goes over to here, transformed to here. Pi goes to pi over 2. So where are my peaks and valleys? 0 obviously stays 0, right? So where are my peaks and valleys now? they're actually in the middle there, aren't they? Where is this? Oh, geez, I kind of missed it there, but you get the idea. Now, where are these happening? Where are the peaks and valleys happening now? Instead of pi over 2, where's it going to be? Pi over 4. Instead of 3 pi over 2, 3 pi over 4. Now, the nice thing is you guys have your great graphic calculators in your hands. So why not? Oh yeah, I did this. Put that over there. That's embarrassing. Let me turn my plot off. And let's go sine 2x. Just to verify, right? You could cheat and go straight here, but don't cheat. Try to visualize it. Try to graph it. I should have done sine of x along with it. Hold on a second. Let me go back and do sine of just x, because that way we can get a good base, sine of 2x. Okay. So the first thing that we're going to see should be the blue. Here's the blue. Here's the red. Do we see, like, remember, all I'm looking at here is just here to here, right? And I could have kept this going too. I guess I can. Oh, it should have gone down to -1. You guys get the idea, though. Okay. If that's not what it looks like, if your graph is messed up, check one thing. Check radians. Make sure that you're in radians and not degrees, because that could throw you off. If your graph looks like this, then something is wrong, right? Very wrong. You should be in radians. You should be in radians. And if you wanted a clearer picture, because my range is -1 to +1, you could go in and change your window to say, okay, instead of, I don't need my y minimum and maximum to go to 10s. Let's just put it to 2. That'll give us a better picture. There's my blue. There's my red. Horizontal compression, right? You see it? Okay, it's compressed horizontally to the inside. You guys have nice colored screens too, but I do not. Okay, so let's go in and try to think about what B would look like. Now, I'm going to manipulate this just a little bit because it might, I don't know, it might help you out to visualize this. Negative sine x plus 1. What's happening there? What do I see as transformations?
Up 1 and then a reflection over the x-axis.
Yeah. Up 1 and a reflection over the x-axis. Yeah. Let's see if that actually happened. Now, I could go in and graph this. Like I could graph this by hand and sketch it, but I think you guys would get the, here. Okay, here. Let's sketch it. There it is. And then it's going to go up 1. Actually, I have to reflect it first, don't I? I have to go order of operations. What's going to happen first if I do order of operations? The reflection of the +1. The reflection, right? So it's going to reflect first. Watch this. This is smartboard magic here. Flip vertically. Flip up and down. Hey. And now up 1. That's what it should look like. Let's check to make sure. I'm going to go in and I'm going to say, okay, there's sine x. Let's do 1 minus sine x. 1 minus sine x. Graph it. So here's our original. There's our new. Okay, got exactly what we thought was going to do when it was going to happen. This is what I'm looking at here. Ooh, pen please. That's my transformed function. Just what we thought it was going to do, right? Now, why do I have to worry about order of operations like that? Because think about it. It's not commutative. Like if I reflect first and then push it up one, it's different from pushing it up one and then reflecting it, right? If I push it up one and then reflected it, it would be all the way at the bottom, wouldn't it? Right? So you have to be a little bit more careful about that. The other way I could have thought about this is if I factored out that negative sign, sine x minus 1. Okay. Then I could have thought it as, okay, so what's going to come first now? A down 1, right? A down 1. Then it would have reflected. So final picture, moving it down 1, then reflecting it up, that's going to actually end up net shifting it up 1. Okay. So you got to think about order of operations. What's going to come first? But again, the goal here is for you guys to look at these equations and say, I think this is going to happen. Based on what I see here, this is what should happen in the graph. You can always use technology to check your answer. Okay, I'm totally fine with that for right now. Another transformation is of some interest is taking the absolute value of a function. Yeah, we never really actually talked about it as being a transformation, but taking the absolute value of something is actually going to make it look kind of cool, in my opinion. Okay. So what's actually going to happen? Well, basically, it's going to tell us that anything below the x-axis, anything below the x-axis is actually going to reflect upward, because anything that's going to come out as a negative is actually going to come out to be a positive, right? Anything that would have normally come out to be a negative is going to shift upward to be a positive. So taking a look here, if I look at my basic x squared minus 1, okay, forget about the absolute value for right now. What's that transformation on the quadratic? Down 1, right? Okay, so that's going to be here. Down 1 unit, there's my vertex. Okay, so here, right? That is just x squared minus 1. Right? That is just x squared minus 1. So what's going to happen if I take the absolute value of that? Well, anything that would have normally come out negative is going to come out positive. So from here up and here up is going to stay exactly the same. It came out positive. It's going to stay positive. But everything down here is actually going to reflect over. It's actually going to look like this. Isn't that cool? Okay, that is going to be my red function. I just think that's pretty cool. How do you show that in your calculator? You do have the absolute value function in your calculator. If you go to math, number, scroll right to number, you see abs. That's absolute value. Okay. So abs of x squared minus, that's x log, whoops. X squared minus 1 should look like this. I'm going to zoom 6 it to put it back to my standard window. There it is. You see that? Anything that was underneath the axis got shifted upward, got reflected upward, I guess I should say. All right. And the last thing that we're going to talk about is, combinations and compositions, I guess. There's kind of two other things. Two functions, f and g, can be combined to form new functions, f plus g, f minus g, f times g, f divided by g, in a manner similar to the way that we add, subtract, multiply, and divide real numbers. We can create, operations of functions just like we do with operations of anything else. So we could add two functions together. We could subtract two functions from one another. We can multiply two functions together. We can divide two functions from one another. Dividing makes it look a little bit more rational, right? What you want to look at is what you want to be careful of is the domain. So let's read this part here. If the domain of f is A and the domain of G is B, so we got two different domains. We're calling whatever the domain is of my first function and then whatever my domain is of my second function. Then the domain of f plus g is just the intersection of A and B because it has to fit both of those domains, right? If I have a specific domain for one function, I have a specific domain for another function, then I just add them together. I have to basically combine those domains. They have to fit both of those two different functions when I talk about f plus g. Okay? The same thing is true for f times g and f minus g. However, it is not true for f divided by g. Why? Because we have to do something additional. We have to say, okay, we not only have to think about the domain of f and the domain of g, but we also have to think of when g is equal to 0, right? Because we can never set g, or g can never come out to be 0 when we do f divided by g. Okay, we can never let g divided by we can never divide by 0. So we have to include within the domain when g equals 0. Okay, we have to be very careful about that. But f plus g, f minus g, f times g, you just have to think about the intersection of the two domains. I have to think about those two domains and say, okay, how do they overlap, or how do they combine to get one full domain? Because they got to be both of the requirements. You know, if I can't be equal to 1 in f, well then I can't be equal to 1 in f plus g. If I can't be equal to 1 in f, then I can't be equal to f, or I can't be equal to 1 in f times g, or f minus g for that matter. The same thing is true for f divided by g, but I also have to think about where g would be equivalent to 0 as well. All right, and then the last thing we're going to talk about is composition. Now, you guys worked a lot with composition. This is kind of like the definition of composition. That operation there, that open circle, that notation for open circle is composition. F, it's actually read F circle G. I've heard people say open circle, F open circle G, whatever. I say F composed in G. Given two functions f and g, the composite function f of g, I say f of g as well. But again, it's the operation of composition, putting one inside the other. I'm taking g and putting it inside f. So f of g of x is f parenthesis g of x. I like this notation so much better, but I can see where its uses are here as well. But f of g of x, that means I'm going to take g of x and plug it in for f. Right? Plug it wherever I saw x in f, I'm going to plug g in. Now, what's important to bring up is the domain of f of g of x. The domain of f of g is the set of all x in the domain of g, such that g is in the domain of f. Okay, so what does that mean? That means I'm going to look at the domain of g. I'm going to look at the domain of the innermost function, and then apply it to the domain of f of g. So I'm going to look at the domain of g, and then I'm going to look at my final answer and say, okay, do I need to tweak that domain at all? Okay, it can't be in, if x is not equal to 1 in g, then x can't be equal to 1 in f of g either. Okay, because you run g first, right? When you think about order of operations, I go into g first, and I run that value first. Then I evaluate f, right? So if x is not equal to 1 in g, x is not equal to 1 in f of g. But if you go and compose the two functions and then you've got something else weird going on, you say, okay, x is not equal to 1, but also this. X has got to be, greater than something else. I don't know, whatever it may be. But you got to look at the domain of g, then apply it to the domain of f of g. You don't ever have to look, if it's f of g of x, you don't ever have to look at just the domain of f, okay, because you're composing g through it. Okay, so let's take a look here. Let's do some composition. Let's find f of g and then g of f. Just to practice here. We got f is x squared and g is x minus 3. Two quite simple functions here. We've got x squared and then x minus 3. All right, so first things first, let's find f of g, shall we? F of g. So f, open circle g, is of x, right? That's the correct notation there, is f of g of x. Okay, let's plug g of x into f of x. So, if you want to continue with that notation, you would say, I'm going to find f of x minus 3, because that is g of x, isn't it? Let's plug it in now. So let's find x minus 3 squared. Okay, let's FOIL that. X squared minus 3x plus 9. Please don't just distribute the squared. Don't do that. And then we have x squared minus 6x plus 9. So that is f of g of x. X squared minus 6x plus 9. All said and done. Please like simplify down all, when you square a binomial or something like that, never leave that squared. Like never leave that as an answer. I always want to reduce it down as much as possible. Okay, so that's f of g. Let's find g of f, just for practice. G, open circle, f of x. So that is now g of f of x. So so f of x is x squared, right? So I'm just going to go into g and plug in x squared. Okay, so in place of x, I'm going to write x squared minus 3. Oh, that's pretty simple, right? X squared minus 3. Some of them are going to be a lot more simple than others. I'm not asked about my domain here because the domain is going to be all real numbers. Thinking about this, like we're going to talk about domain here in a second. How do you think about domain? You look at the domain of G. So like the domain of G is all real numbers, right? Just linear. Then I would say, okay, let's look at the domain of the full. Do I have to tweak that domain at all? No, it's still polynomial. It's all real numbers. So the domain is always all real numbers here. What if I flip that around? Is that going to change anything? Well, now the innermost function is f. So I got to look at that guy first. X squared. Okay, still all real numbers. Okay, good. Do I have to tweak that at all with my final? No. Still polynomial. All real numbers again. Let's take a look at something that would change a little bit. So we've got radical x and radical 2 minus x. Obviously things that are going to have a weird domain, a tricky domain, right? My domain's going to get a little funky. F of x is radical x and g of x is radical 2 minus x. Okay, first things first, let's find f of g. F of g. Okay, so f of g of x is going to look like this. F of g of x is 2 minus x. So that means I'm going to have the square root of, see, it was the square root of just x. So now it's the square root of 2 minus x. Oops, I forgot my square root. Anybody know how I would simplify that down? Or what I could do to simplify that down? Some people might just leave that and say, there's something else to do. Anybody know what I would call that? That's actually the fourth root of x, right? The square root of the square root. That's the fourth root of x. Or sorry, fourth root of 2 minus x, 2 minus x. But if you have a square root of a square root, that's the fourth root. That's like power on a power, right? Multiply powers. Square root on a square root, multiply those indices. So there it is, fourth root of 2 minus x. That's f of g. Now let's talk about the domain. Now for my domain, I got to look at g of x first. What is the domain of g of x? Well, I have to say 2 minus x has to be greater or equal to 0, right? Okay. Well, let's add x over to the other side. So 2 greater than or equal to, I should have done this over here. 2 greater than or equal to x, so flip that around. X has to be less than or equal to 2. That's my domain of my innermost. Okay, so I have this domain of x has to be less than or equal to 2. Do I have to change that at all once I look at my final answer? Okay, 2 minus x, still inside. So if I were to try to look at the domain of this, I would say, well, 2 minus x has to be greater than or equal to 0. Didn't I just do that? So I'm looking at the domain here, and it essentially is the same thing. Less than or equal to 2. So domain is going to be negative infinity to 2. bracket on 2. So I looked at my domain of my innermost, but then I didn't even have to change it at all in my final. Okay, let's take a look at B. Let's find G of F. So G of F of X. Okay, so this is the G of the square root of X. Okay, so that is going to be the square root of 2 minus the square root of X. Now that I can't simplify at all. That's it. That's it for that one. Now, I look at my domain here, and what is my innermost function now? My innermost function is F. What is the domain on F? Greater than or equal to 0, right? The domain on F is greater than or equal to 0. You know, just writing it up here, the domain on G was X is less than or equal to 2. So what I'm going to do is I'm going to look at the domain of F. So I know I've got to be greater than or equal to 0. And now I'm going to look at the domain of G of F. Okay, so in here, I know that 2 minus radical X has to be greater than or equal to 0, right? I have in the back of my mind that X has to be greater than or equal to 0 because that was my innermost. And now I'm going to say, okay, well, let's add over to the other side. So 2 greater than or equal to the radical X, and I square 4 greater than or equal to X. So I know X has to be less than or equal to 4. So I not only need to stay above 0, but now I need to stay below 4 as well. Do you follow me there? In the back of my mind, I knew that F had a domain of greater than or equal to 0. Then I apply that domain in conjunction with the domain of G of F. So looking here at my final, okay, the domain of this guy has to be less than or equal to 4. I've got to put those together now. Okay, so I've got to stay less than or equal to 4, but still greater than or equal to 0. So my domain in this case is 0 to 4. I'm going to do C right here as well, which is F of F, which is F of the square root of X. Okay, so it's the square root of the square root of X, or the fourth root of X. Now in this case, my innermost function was F, right? The domain on F was greater than or equal to 0. Do I have to change that at all when I look at my final answer? Is it still greater than or equal to 0? Yeah. So my domain is 0 to infinity. It's got to be greater than or equal to 0. Okay, let's do G of G. Now this one's a little bit more tricky if I remember correctly. G of G. Okay, so we've got, put it down here. I'm going to scroll down in a second, don't worry. Just want to write down the original. So G of X is going to be G of radical 2 minus X. Right? Okay, so that's going to be the square root of 2 minus the square root of 2 minus X. That's G of G, right? That's not so bad. That's not the difficult part here. The difficult part is going to be looking at its domain. Okay, so the domain of G, we said earlier on, was X is less than or equal to 2. Domain of G, I'm going to write it out here. Domain of G is X is less than or equal to 2. Now I got to look at the domain of G, right? I looked at my innermost function. I said, okay, I know that X has to still be less than or equal to 2, but now I have to look at my final. And in my final, I know that X has to be less than or equal to 2 still, but still now here, 2 minus radical 2 minus X has to be greater than or equal to 0, right? My piece underneath the radical still needs to be greater than or equal to 0. So let's evaluate this. Let's just add over the radical, square the 2, subtract, oops, sorry, no, that's a minus sign in the middle there. Subtract the 2. So divide by -1, which forces me to flip the symbol. So -2 less than or equal to x. So that's going to be x is greater than or equal to -2. Okay, so that's, now I have to say greater than or equal to -2, but still less than or equal to 2, right? I have to look at my domain of G and combine it with my domain of G of G. So in this case, my full domain is going to be -2 to +2. The bracket on the right side, the 2, +2 came from domain of G. Being bigger than -2 came from the domain of G of G. You're going to find that doing the composition now is not that difficult. The only difficulty it may be is like maybe when you got to like cube something, you got to work out the, multiplication or whatever. Maybe you're simplifying. The difficult part is going to be the figuring out what the domain should be. All right. Last couple things here. Let's do one more composition. Now, composition isn't just limited to 2 things. You could put a function in a function in a function, right? You could keep that, you could chain that together as long as you wanted to. But let's look at this one. Let's find f of g of h. And I'm given those 3 functions where f is a rational, g is an x to the 10th, and h is just a plain old linear. Okay, so here's what the notation is saying. I want to find f, I want to find g, and I want to put h in all those. Okay? That's f of g of h. All right, so let's keep putting it in. So this is going to be f of g of h. H is x plus 3. Okay, let's find g of x plus 3. Well, g of x plus 3 is just x plus 3 to the 10th power. Now, I'm not going to let's not multiply that out. Let's say both of us some time and mental pain of multiplying that out. So now let's find f of x plus 3 to the 10. Okay, so that means, look at f here. I've got 2 x's. That's going to be x plus 3 to the 10th over x plus 3 to the 10th plus 1. And there we have it. I'm going to leave that there just so you can see each piece. If I was going to be very mean, I would make you reduce all that, but we're okay. If you ever have a question on like, should you reduce it down or should you simplify down like during a quiz or test, that's an okay question to ask. I can say, yeah, you need to keep going, or like you need to keep simplifying or not. Because soon are the days where it's going to become like, okay, we're not going to need to rationalize the denominator as much, and like taking something to the 10th power. I mean, I'm not going to make you do that. All right, last thing. Let's work it backward. Say we're given a function and we wanted to decompose it. We're looking at, okay, what are the pieces and parts inside there? Like, for example, here we got capital F of x is equal to cosine squared of x plus 9. Let's find functions f, g, and h such that capital F is f of g of h. All right, so now one of the key things to remember here is that cosine squared of x plus 9, that notation really means this. right? That notation of putting the squared next to the s on the cosine is just saying, okay, I want to square, that's like having two cosines of x plus 9s multiplied together, okay? The reason why we do that notation is so that we don't just get sloppy and write it like this. Because what does that imply? That implies squaring the x plus 9, which is not algebraically correct. Okay? But I'm going to put it back to this because that's going to help us decompose it. What's my innermost function? What's my innermost function here? X plus 9. And there's my h. So h of x is x plus 9. Okay, peeling back that layer, like going from inside out. Okay, what is g of x then? Be careful, what is g of x? Just cosine x, right? Just cosine x. Don't say cosine x plus 9. The x plus 9 was h of x. Just cosine x. And what is f of x then? X squared, good. X squared. You don't see an x squared there, right? You don't see it there because it's not x anymore. The input is changed from x into g of h, right? And g of h is cosine x plus 9. And you don't just see a plain old cosine x because it's not just cosine x, it's cosine h of x, which is cosine x plus 9. Good. Alrighty, folks, that's it for section 1.3. Let me turn off the video.